Hello everybody, this is Dr. Christopher White and welcome back for part 3 of our video dealing with the lab exercise correlation. So we've now moved on to part 2 of the lab exercise, and this is going to deal with geophysical correlation. So the use of geophysical data to correlate between different locations. This can be from borehole to borehole, or it can be using seismic sections. So the first part is going to deal with boreholes, and if you remember, boreholes are commonly used as a method to access rocks which would otherwise be inaccessible due to cover. So it's a method that's used by a range of different companies, including mining companies, oil and gas, water, environmental companies. And essentially what you want to do is obviously you want to drill down and you want to analyze the rocks that you are passing through as you drill downwards. Now, there are a number of ways in which you can bring this information about the rocks back to the surface. One of the more common ways is using mud logging. So the mud, or drilling mud should I say, is a material that gets injected down as part of the drilling process, and it's used to lubricate the drill bit as it passes through the rock, and it's also used to maintain the integrity of the borehole itself so it doesn't collapse. Now, the drilling mud will actually bring material back up with it, and so as the drill drills down, as it passes into a layer of rock, it will start cutting up that rock. Pieces of that rock will then come into the drilling mud, and then it will be returned to the surface. And then what can happen is a geologist can come along and they can log the mud, so they can look at it and say, right, what minerals are present? Are there any pieces of rock present? And this is going to give you an idea about the rock that's being passed through by the drill bit at that time. Another method you can use is something which is referred to as rock chip logging. And in this case, as the drill bit drills down, chips of rock are produced by the drill bit and they are returned to the surface, often using compressed air. And in this case, you have an incomplete piece of rock, but you do have chunks of the rock that the drill bit is currently moving through. So once again, you can analyze the rocks that the drill bit is going through, allowing you to know, what material it's passing through. The final method is the most expensive, and this is diamond drill core. And this is the method that will actually produce a cylinder of rock. So a special drill bit is used that doesn't completely destroy the rock as it drills through. Instead, it cuts around the margin of a cylinder, and that cylinder can then be returned to the surface, and then the rocks which make up that cylinder of rock can then be logged. Now, diamond drilling produces this consistent chunk, this consistent length of rock. So you can measure, the thickness of the layers. You can look at the types of rock present. You can look at the alteration that's present. You can also look at things like the angle, the dip of the rocks that the drill bit is passing through. So this is giving you a lot more information, but recovering an entire cylinder of rock, sometimes from hundreds or maybe even thousands of meters down, is obviously a very difficult undertaking and therefore quite expensive. So this typically leads to a situation like we see with the diagram on the left. So we're going to be using this diagram as part of the part 2 questions. But what you can see is we have 3 different locations. In the first location, we do actually have a full stratigraphic column showing you the layers of rock that are present. However, when you're on to the second and the third location, you will notice that that stratigraphic column is now missing. That's purely because what you'll do is you'll spend your money drilling one good borehole so you know the rocks that are present, and then the rest of the boreholes will be a lot quicker and a lot cheaper to do. But as part of that process, you won't really be monitoring what rocks you're passing through as well as in as greater detail. And so in situations like this, what you will instead do is you will drill your borehole and then you will pass down your geophysical tools down the borehole to analyze the properties of the rocks. And then what you can do is you can actually look at the properties of the rocks and you can compare them to the properties of the rocks from the location for which you have a complete stratigraphic section. And so this is the kind of process that you will find occurring quite a lot, especially in the oil and gas industry, where this is a relatively common process. You'll take a few boreholes so you know the actual stratigraphy, and then the rest of them will often be a lot faster and therefore a lot cheaper to drill, and then you'll use geophysics to actually correlate the rocks between those boreholes. So When we look at the data which is produced by a geophysical survey of a borehole, you are going to end up with something that looks a little bit like this. Now remember, the data being produced is comparative. So in the case of question 1, we are going to be looking at geophysical data from 3 separate boreholes. And the geophysical data we'll be looking at in particular is resistivity on the left and spectral gamma on the right. So you will notice if we zoom in on this diagram here that you have peaks and you have troughs in the data. And these peaks and troughs correspond to different layers of rock. And whether you have a peak or a trough depends on the type of rock. So in the case of resistivity, we've already discussed how rocks like limestone and sandstone are naturally quite resistant. They don't let an electric current pass through them easily. In contrast, mudstones show far less resistance, comparatively speaking, and so they can conduct an electric current far more efficiently, so they have a lower resistivity. So if we look at the example borehole over here on the left, you can see we have a layer of mudstone and we have a low resistivity, another layer of mudstone, low resistivity, mudstone, low resistivity, etc. You will also notice that when we come across a layer of sandstone, the resistivity peaks quite clearly, and we can see that repeated again and again. And then we also see here we have a layer of limestone. And in this particular instance, the limestone is producing a kind of intermediate resistivity. So it's not as resistant to an electric current as the sandstone, but it is more resistant than a mudstone. So the data puts the limestone layer at somewhere in between. And so what we can do with this resistivity data is we can say, right, this is going to be a sandstone, and it also gives us a gauge of the thickness of that layer as well. So you can see how we're already gathering information about what types of rocks the geophysical tools are passing by. Now over here on the right, we have the spectral gamma. So if you remember, spectral gamma is a measure of how many gamma rays are produced by the radioactive decay of isotopes within a layer of rock. So going back to what we discussed earlier in this video, of course, limestones tend to have relatively few radioactive isotopes associated with them, so they tend to produce the lowest amount of gamma rays. Sandstones will very often have some minerals that contain radioactive isotopes, such as zircon or monazite, and so sandstones will produce a kind of intermediate amount of gamma rays. And mudstones will be rich in clay minerals, which are often relatively potassium rich. And one of the more common radioactive isotopes in the Earth is potassium-40. So mudstones tend to produce the most gamma rays versus the other two types of rock. So once again, when we look at our readout for the amount of gamma rays being produced by each layer, you can see that in terms of the mudstones, so you can see one here, here, and here, you can see that they are producing the most gamma rays. You can see for the sandstones, they are producing an intermediate amount of gamma rays. And in the case of the limestone down here, you can see that it's producing the least gamma rays of the 3 types of rock. Once again, the size of these peaks and troughs are giving you some indication about the thickness of each of the layers. Now, in the case of this column over here on the left, you can correlate the peaks and troughs to the layers of rock relatively easily because there is a stratigraphic column provided. However, if we look at the column over here on the right, you can see that the stratigraphic column isn't there anymore. So all we have are the peaks and the troughs for the resistivity and spectral gamma. Now, the first thing you will notice is that the peaks and troughs are not exactly the same. So for instance, if we look at the resistivity data here, we can see that we have an obvious peak, then we have a trough, same trough there, then we have another peak, then we have another trough, and then we have another peak. But you'll notice that this third peak is noticeably thicker on the second log. So this is indicating that the sandstone layer that we see here has clearly increased in thickness between these two locations, hence the increased thickness of the resistivity plot, the resistivity peak, should I say. Now, in order to correlate between these two locations, what you have to do is you have to look for the same features in the data. So, for instance, over here on the left-hand column, you can see we have a boundary marked out here in red. So we have a formation above the boundary and a formation below the boundary. And I have selected this to be the boundary of between the two formations. So over here in the spectral gamma, you will notice you obviously have a peak, a trough, etc. And then when you're coming towards the boundary, you have this quite large peak, followed by a drop to kind of like an intermediate. And then we move into the limestone, and then we have the lowest amount of gamma ray production. So we're looking for a stepped decrease in the amount of gamma rays. So when we come over here to our right hand column, we can see the same peak. In this case, it is smaller, but it is still there. We can then see this intermediate point, which is going to be our layer of sandstone. And then we have our low point here, which is going to be our limestone. So we can see our transition from mudstone to sandstone to limestone. And this stepped decrease in the amount of gamma rays being produced helps us to show, right, this is where the boundary sits at this location, even though we don't have the stratigraphic column to go along with it. Now, over here on the the left hand side of the right hand location, the second location, we can see that we have a situation where we have this peak in the resistivity, followed by a trough, followed by a peak, then followed by this intermediate trough. Okay, so once again, this is our layer of limestone. So this is helping us to work out where we are. So over here, we can see here's the trough, here's the peak for the sandstone, and here's this intermediate trough for the limestone. We see the same thing here, so therefore we know where our boundary sits. So even though we don't have the stratigraphic information to go along with this data, we can use the data itself to mark the position of the boundaries. So if we look at the diagram that's going to be used in question 1, you can see that there are several formations noted. So formations A all the way down to formation H. And it's going to be your job to find these boundaries at the other two locations. I'm going to repeat that again. You are looking for the boundaries. You aren't trying to pick individual layers from one borehole to another. You are looking for the position of the boundaries. Now, one of the things that can happen is if your sequence is being deformed in some way, obviously that's going to cause the relative height, the relative position of these formations to rise or fall relative to your starting location. So for instance, you could have formation B is located this level at our first location, and then maybe let's say there's a syncline. Okay, so that means the second location here has been dropped down because it's towards the axis of the syncline, and then over here at location 3, it's going to be slightly higher because it's on the other side of the syncline. So you would have a trough-like feature. And so that would mean that formation B for this second location would drop down relative to its position at location 1. So don't just expect the formations to continue straight across. Okay. The other thing is that, as previously touched on, the size of these peaks and troughs will change. But what you're looking for is you are looking for distinct changes. So for instance, if we look at this column here, let's look down. Okay, we can see that at the boundary between formation C and formation D, we have a very distinctive little peak there where we have these two peaks for these small sandstone layers and a trough in between them representing a mudstone. Okay, that's quite an obvious thing you can look for as you work your way across. The same thing here for formation E. You can see you have this very distinctive peak, trough, peak, spectrum here. And you can see it's going from essentially high resistivity to low, high, low, high. So once again, you can look for this same pattern. And over here in the spectral gamma, you can see you have the reverse situation where you're going from intermediate to high, intermediate to high to intermediate. So once again, you're going to look for that pattern on the column here, and you're going to say, right, if I can locate this same pattern, the peaks may be of slightly different width, but keep an eye out for them. They'll still be there. That will then allow you to correlate the position of formation E in at the borehole, or in the borehole taken at location 2. So what you're going to do is, as you come across to the second borehole, you're going to find, let's say, where the formation A, formation B boundary is. You're going to mark it. So let's say, for argument's sake, it's right there. You're going to mark the position just with a straight line. And then you are going to correlate. So you're going to draw a line between the two locations, between the two boundaries. And that's going to be your line of correlation between the boundary for formation A and formation B at location 1 and location 2. So this is the way that we are essentially correlating between our boreholes, even though for locations 2 and 3, we don't have the stratigraphic column to go along with them. Okay, so if we come down now, so for question 2, it's going to ask us, does your correlation indicate any deformation of the sequence? Okay, so remember, if the sequence has been deformed, and this could be either folding or faulting, it's obviously going to change the relative positions of the boundaries between the different formations. It's going to push layers of rock up or move them down. It might, as part of that could be either due to folding or faulting. So if, for instance, you notice that, let's say, the boundary between formation A and formation B falls here at location 1 and then falls here for location 2, well, that would suggest that location 2 has dropped relative to location 1, and of course that would be an indicator that the sequence has been deformed. So for question 3, it says, based on your answer to part 2, question 2, what kind of deformation has the area experienced? So if you remember, so in the event that you have perfectly level boundaries between all 3 locations, obviously no deformation has occurred. There's no folding, there's no faulting. Now, in the event that you do spot some kind of feature that you believe is indicative of deformation, well, in the event of tension, which is stretching your layer of rock, you would probably develop something like a normal fault. And so in the position of a normal fault, what you might see is, for instance, let's say for argument's sake, the normal fault falls about midway at location 2. So if you remember, for a normal fault, the hanging wall will drop down relative to the footwall. So if we imagine the hanging wall is the upper part of location 2 and the footwall is the lower part, what we would see is the beds, or the boundaries between the formations, should I say, will correlate horizontally for the footwall because they haven't been deformed. But then you will notice that the boundaries for the hanging wall will have dropped down because that block of rock is dropping down relative to the footwall. In the case of compression, well, that's going to result in either thrust faults or more likely folding. So in that case, what you're going to see, if it's a fold, is you're going to see the boundaries between the formations going up if it's an anticline and then coming back down. Or on the other hand, if it's a syncline, you're going to see the boundaries going down and then coming back up again. So once you've correlated between the other 2 locations, so once you've correlated between 1 and 2 and 2 and 3, you're hopefully going to see a pattern in the correlation that's going to suggest to you that something has or has not happened. So you're going to have to work that out for yourself. So for question 4, we are going to be looking at a seismic section. And I'm actually going to come over here to the Adobe document, and I'm just going to rotate things back where they need to be. And I'm going to drop down here to our seismic section, and here it is. And so it might look quite intimidating, but this is a relatively straightforward seismic section. So straight away you can see in this left-hand region, you can quite clearly see multiple layers. And you can quite clearly see multiple layers over here in the right-hand region. And then in the center, well, it kind of gets rather hazy. It becomes very homogeneous. The layering disappears. And so clearly something is going on in the middle of this seismic section. So for question 4, what you're going to do is you are going to correlate 6 layers either side of the diapir. Okay, so a diapir is simply the result of compression. And what's happening is further down the sequence, below the level of this seismic section, there's a layer of salt which is being compressed by the rocks above it. And if there's some kind of weakness in the layers of rock above it, that compression of the salt will actually cause the salt to flow upwards along this weakness, and that results in a diapir. Okay, and so we can see this diapir here, right there in the center of our seismic section, as this region of very homogeneous seismic returns. So it just looks fuzzy. There's nothing going on there. You can't see layering because the layering has been destroyed by the rise of this diapir. Now, either side of the diapir, the layering is visible. So for question 4, like I say, you are going to correlate 6 layers on either side of the diapir. Okay, so initially what we had is a nice horizontally bedded sequence of sedimentary rocks, and this diapir comes up through the sequence. So you'll have the same layers of rock on either side of the diapir. So what you're going to do when you are analyzing your seismic section is you are going to look for the strongest reflectors. So you're going to look for the layers of rock which show this rather distinctive, very strong dark color. So you can see a layer right here, which is a wonderful example. This layer is a very strong reflector. It, you have this nice thick dark line. Okay, so this is on the left hand side, and then when you come over here to the right hand side, there it is again. Okay, so straight away you can see that layer is located at, well, approximately the same level. And so how would you correlate them? Well, you will correlate them by highlighting them in a distinctive color. So you can see in the example diagram here, a layer has been highlighted in blue and the same layer has been highlighted in blue on the other side. Same with these layers here, highlighted in yellow here and yellow on the other side. Now, one thing I would ask is please don't use the 2 layers that I've highlighted here when doing your correlation. Find 6 completely new ones. Okay, so that's a relatively straightforward thing to do. Like I said, please do 6, and it's very strongly advised for you to use different colors for each layer if you can. Please do not mark them using pencil, because obviously if you just draw a grey line here using your pencil, well, when you scan the document or when you turn it into a, once you've drawn the line, you scan it and you turn it into a PDF and send it to me, that grey line is not really going to be visible. So I'm going to assume that you haven't correlated and you're not going to get any marks. So please use colour to highlight the layers that you are correlating. And if possible, use 6 different colours, please. So question 5 asks you, has the sequence been deformed and how can you tell? So the first thing is a diapir has smashed through the middle of the sequence. So there's a pretty high chance the sequence has been deformed. So remember, deformation is going to result in the bending of layers. So you might see folding, okay? And it can also result in the displacement of layers. So you may see layers at different levels on either side of the diapir. So coming back to the layer that we were just talking about, you can see the layer right here on the left-hand side, and you can see the same layer right here on the right-hand side. But you'll notice straight away that the level of these 2 layers appears to be different. So you can see the average level is going to be somewhere around here on the left-hand side, but then it drops down clearly on the right-hand side. And that would suggest that there may have been some kind of displacement due to the diapir moving through. So this right-hand block may have dropped down slightly relative to the left-hand block. You can also see that there is clearly, the bedding is clearly no longer perfectly horizontal. And so that would also give you an indicator of whether the sequence has been deformed or not. Because remember, these layers of sedimentary rock will have initially started as nice horizontal layers. Okay, and that is then it for the lab exercise correlation. Okay, thank you for watching everybody and have a good day.